Good morning. I think we are ready to start. Welcome to the morning session of the second day of this interesting workshop. Our first speaker is Stefano Trillo, graduated from La Sapienza, as I just learned, and worked in Tucson for a while. And well, his talk is over there. He's done fundamental works in nonlinear optics, and I think he welcomes questions during his talk. Okay, so please turn off your devices because they cause interference, and take it away.
Okay, thanks for the introduction. Can you hear me? Yes, I think so. Okay, so title is From the Riemann Problem to the Focusing Catastrophe Observation in Nonlinear Optics. And this is mainly a work I've been doing while visiting in Lille, group of Arnaud Mussot and Kudlinski, work done by the former postdoc Bendhamane and Xu, and also on the focusing part by Eric Louvergneaux and then Hélène Louis, and some theoretical work done in collaboration with Matteo. So first of all, I want to acknowledge the organizers for inviting me, and this happens to be essentially 10 years after the first meeting we had on specific dispersive shock wave back in Trieste in 2012, and it was organized by Moro. And for those who are old enough, you can recognize that this is an LP cover for a very famous band of the 60s, 10 years after, who performed live in Woodstock. And the wish is for us is to be naturally live after COVID. And the outline is very simple. So I will make a brief survey of the results that we had in these last 10 years in optics on dispersive shock waves. This is essentially defocusing NLS stuff. And then I will focus specifically on an experiment, which is the Riemann problem, looking at phase transition of the flow. And it's actually a double experiment because you will see, but we do a first experiment which is dam breaking, essentially the problem of dam breaking, and a second experiment which is much more difficult, which is a piston problem in a gas. And then at the end, I will briefly mention some issue on the focusing catastrophe. So assuming that we are in the golden age of nonlinear optics for dispersive shock wave now, going back to the, actually, I don't know why I see the bar. Well, doesn't matter. Going back to this, what I call Stone Age is the 80s, where people were launching simply pulses along an optical fiber with normal dispersion, and the governing equation is the defocusing NLS. And they do see actually steepening and onset of oscillations, but they were very tiny at the beginning. And the field remained silent for a couple of years, actually for 3 decades. And in 2010, it was rediscovered in space. So in this case, you have a spatial experiment, diffraction. So dispersion is substituted by diffraction here. And you can see that the signs changes, plus and minus here, minus and plus here. But the physics remains the same because it's still defocusing NLS. So you can see an experiment by Jason Fleischer group where they do see dispersive shock wave 1D and 2D and their interactions. And we also did an experiment the same year looking essentially at what was known as a phenomenon of thermal blooming. So you send a laser in a medium with thermal nonlinearity, and you can see that it broadens a lot and steepens in the fronts. And we interpreted this as a dispersive shock wave phenomenon, but in a non-local medium, which is quite surprising because shock is a very local phenomenon. Okay? And using this thermal medium, we also moved to another experiment, which is looking at the evolution of a hyperbolic tangent input and looking at the catastrophe of this. And this is very important for two reasons. Because in the local case, this is a purely solitonic dispersive shock wave. So essentially, it's a reflection-less potential. And you can use inverse scattering to predict the number of solitons that emerge. And the other one is that in terms of breaking, this is a non-generic breaking. And we did the theory with Antonio Moro back in 14. Another experiment we moved on, which I think is very important, it was actually looking at the wave breaking and shock waves for periodic waves. And in optics, we call Fourway mixing, because then now you inject two lines, two frequencies, and you generate all the odd harmonics. And in the shock regime, you can have many, many harmonics, up to 50, okay? What was the experiment about? We launched actually a cosine wave, which is two-line in Fourier space, of course. And after 6 kilometers of fiber, we look into this dispersive shock wave. And we were able in this experiment actually to map the evolution, because you can do the experiment for many different powers, actually input power here. And this maps into the evolution, because the normalized length is the physical length times the nonlinear coefficient times the power. Okay, so looking at different power means to look at different normalized distances. And you can see that actually the experiment is in very well agreement with the simulation, with the NLS prediction, actually. And the breaking is a breaking that it reminds of the breaking for the hyperbolic tangent. So what breaks is in the null of the cosine at this point, and then you get these filaments. And these filaments are actually bands, because you are in the periodic domain, so you use finite gap approach. But for very high power, this can be considered as solitons, actually, because the bands are very narrow. And if you do the experiment with an asymmetric input, two lines, but with different power, you don't get this zero velocity filaments, but you get similar physics. Okay, now this experiment actually reminds of exactly of the Zabusky and Krashkal very famous numerical experiment in '65. And back in 2015, we were astonished by the fact that nobody did the real experiment interpreting it in terms of IST, inverse scattering. Okay, so we tried that with a bunch of good guys in waterways, Miguel Honorato, Min Chub, and with the help of Gino Biondini for the IST part. And this was actually the same slide shown by Gennady yesterday. So you can see that this is KDV after all, it's not defocusing NLS. So you break on one side of the cosine and you generate these solitons. And actually, we were able to interpret this in terms of inverse scattering using a WKB approach, because inverse scattering here is not trivial at all, because you are finite gap, is a periodic problem, and you are in the semi-classical limit. So small epsilon means many solitons in your input. Okay, so WKB gives this curve, these stairs, and the dots, I mean, are different experiments with different water depth h. And you can see that the experiments follow pretty much the expectation from WKB, except when you get a very high number of solitons. We got up to 13 solitons, where you can see some deviation because of dissipation is entering your system. Okay, let's move. I don't know why this is not working. Let's move on. Sorry about the fact that you cannot read the. Can we do something about Yeah. Meanwhile, I can speak. Okay, so next problem, very important problem in my view, it was actually to. No, it's okay. We leave it like this. I will read the title.
What if it shows up here?
It shows up it's a problem with Zoom, I guess.
It's not here.
No, it's not my screen, it's Zoom's.
Yeah.
Yeah, so the view is not.
Can't click it. Yeah,
Sorry about that. Not my fault. Okay, so this is another important issue in my view. When you take defocusing NLS and you perturb, and the perturbation here comes from next order dispersion, so third order. And this is actually a frame that reminds, for those who know, this Kawara equation in the framework of the KdV. Essentially, this terms is making the shock to radiate. Like solitons, actually. This is very well known for solitons. And in standard, I mean, if this is small, if this coefficient beta 3 is small, the radiation is small. You can see the radiation occurs at a precise frequency. And this frequency you can predict by a phase matching argument. So essentially, it's the dispersion operator equal to the nonlinear wave number of the shock in this case. And in this formula, what matters much is the velocity of the shock, because the velocity of the shock is always different from zero, very big term. And usually you use here in the formula the velocity of the leading edge of the shock. But if beta 3 is large enough, then what happens is that you modify, you can see that there are two shocks actually, one here, one here. You modify a lot this shock, and it becomes a front here, and this velocity becomes the Rankine-Hugoniot velocity of the shock, not the dispersive one. So it's a quite interesting phenomenon. And this is exactly the situation where the radiation grows much larger. And one way to enhance this phenomenon is to introduce in your system an artificial engineered periodicity along the longitudinal variable z, which is always z in optics. We did an experiment again in Lille on that, and you can fabricate this so-called topography fiber. So it's a fiber where you modulate the core, so it's a periodicity in z. And the periodicity in z is of the order of 1 meter. It's this term here, lambda capital. And OK, you can see that, in fact, now the phase matching condition for the radiation changes because you introduce a quasi-momentum due to the periodicity. And you can have more than one line. For the shock, we get 4 lines here. And the lines are exactly where you predict. And you compare this to the soliton, because you can excite in the same system, just changing wavelength a soliton instead of a shock, a dispersive shock, actually. And for the solitons, you can see many radiation frequencies, actually. OK. Last experiment I want to mention, which is very important for the rest of the talk, is actually something we did on explaining why, at the beginning of the nonlinear optics in the 80s, the oscillation part of the dispersive shock was so tiny. And the reason is that, in fact, usually in optics, you work with pulses that goes to 0 at infinity in time. Whereas if you introduce a pedestal, a background of the pulse itself, then you can have a great enhance of the shock effect, at least the oscillation trains. And you can see that, OK, so this is 0.1% of the background. You can see this is numeric, this is experiment, again, in very well agreement. You increase the pedestal, you start to see enhancing of the shock. Again, experiment and simulation, and up to 6%, where you can see a very well-developed shock. And in fact, if you go in and looking into the contrast, which is the ratio, the maximum to the minimum of the shock, you can see you reach a maximum here, 100%, exactly at 6% of the background. And then it slightly decreases, actually. And you can see that actually this point is the point where you get cavitation in your dispersive shock wave. So the bottom line goes to 0. And this is very important for the Riemann problem. Okay. A little bit of equation. Okay. Defocusing NLS, just to, I mean, I don't have to remind perhaps to this audience, but just to fix the idea. So we get the defocusing NLS in the fiber formulation. We write it in semi-classical way. So this epsilon is a ratio of the nonlinear length to the dispersive length, and it's a small quantity. And actually, you use what is called Madelung transform. So you write psi as the square root of rho, which is power in the context of optics, an integral of u divided by the epsilon, and this is a frequency jump. So power, rho, and u, which is in our units is frequency or chirp, frequency chirp is called in optics, are actually equivalent to the density and velocity of a gas. So actually, with this transformation, you write as usual the NLS in this form. So you have a black part, which is totally equivalent to shallow water equation or Sandvenander, called by the engineers, or a P system in a gas, where rho is elevation of water or density of the gas, and u is velocity again. And of course, this is a conservation law. And this is ruling the occurrence of the shock, because it's a hyperbolic system. It's a shock driving force. And of course, you can diagonalize and use Riemann invariant. And this part is a dispersive part, which is responsible for the regularization in terms of onset of oscillations. Okay, so usual stuff here. Let's focus essentially on the hyperbolic part for a moment. So hyperbolic part, we can, of course, we can say everything about the shocks, and you can have two shocks, one going to the left, the other going to the right. So NLS is a bidirectional system, contrary to the KDV, which is unidirectional. And in order to find the shock, actually, you impose what is called Rankine-Hugoniot condition, which is vectorial in this case. So Rankine-Hugoniot's usual formula is this, and Q is rho times is a bicomponent field, rho and rho u. And actually, the shock velocity Vs is fixed by the jump through the flux, of course, the numerator. And what is important here to notice is that you have four arbitrary quantities, the right and left, u and rho, and three quantities are free. The fourth is assigned by the condition. And what is important to keep in mind is that shocks have a related jump in power and frequency. They cannot be arbitrary. Okay? I don't have. I will go very, very briefly through this because the audience know Wheaton theory, I guess, I assume. There was a specific workshop. So if you take the classical shock of the hyperbolic part, then you can do modulation theory, Wheaton theory, actually. And you can describe this dispersive shock wave in semi-analytical terms. How you derive a rarefaction wave of the Wheaton equations, which are 4 for the NLS. And this rarefaction wave is what gives the modulation of the parameters of this dinoidal function, which is the oscillation, essentially. So you have 4 parameters here, lambda 1, lambda 2, lambda 3, and the modulus of the elliptic function m. And they are slowly modulated from m equal 1, which is a soliton edge, to the linear edge where the amplitude of the shock goes to 0. And this actually can be thought of as a gray solitons in all senses. Okay, so far so good. But Wheaton theory is an asymptotic theory. Asymptotic here means either asymptotic in time, so great evolution distance for us, or asymptotically in the sense of epsilon going to 0. But actually, I showed this slide because Wheaton theory is actually very good to fit even at finite time and finite epsilon. So here is a comparison between the Wheaton asymptotic, which is analytical in rho and u, and what you get from the numerics if you start from the shock. So pretty good agreement. Okay. Here is the blue and red is the classical shock you start from. Okay, next. So Wheaton theory actually assuming its basic application that you start from a classical shock and you do the dispersive regularization. But we wanted actually to go one step further and say, okay, what about if we take a generic step initial condition, and this is a Riemann problem. So you have a jump in, essentially a jump in rho and a jump in u, and then here it comes the Riemann theory actually. And to appreciate the importance of the Wheaton, of the Riemann work, that was 2 centuries ago, this date. I quote John von Neumann, which 1 century later said that the only things of any degree of generality that we possess is a classical discussion by Riemann, and this is strictly 1D and strictly isentropic. Okay, that's fine for who does fibers, because fibers are 1D, they are isentropic, there is no entropy to take care of. And also, one more thing, in fibers we have a pressure which is proportional to rho square. Okay, how we solve an arbitrary step in a generic conservation law? Riemann tells us that if you have a 2-by-2 system, as in our case, the evolution can be given in terms of wave pair. Each of the type, shock wave or rarefaction wave. So actually, rarefaction and shock are the building blocks of your generic Riemann problem, okay? And so rarefaction is, of course, a smooth solution. So essentially, Riemann says that you can have 3 cases, rarefaction, rarefaction, shock, shock, and rarefaction, shock. And if you add dispersion to this system and you go back to the full NLS, then you have exactly the same thing, except you replace the word shock with dispersive shock wave. So essentially, you have again these 3 cases, okay? Okay, what was the motivation to do the Riemann problem? The motivation was twofold. First of all, we wanted actually to challenge Wheaton theory. Wheaton theory, generically, it's difficult to compare if you start from a generic smooth initial condition. So essentially, we wanted to see whether in an experiment we can actually challenge the theory to its extreme consequences. And the second one is from optics, actually, because you have square pulses, what is called non-return to zero pulses, and multi-level modulation, and these are actually described by step initial condition. And the third one is from the physical point of view, because the Riemann problem is actually equivalent to 2 canonical problems of fluids. The first one is the dam break flow, and the second one is the piston problem. Oh, by the way, I mean, this is this is the first experiment we did in 2017, and this actually came out in 2022, so this year, a few months ago. And actually, we submitted this paper to PhysRevX, PhysRevLetters, Nature Physics, Nature Photonics, and it was rejected by the editors without reviewing. And we didn't have the word Riemann in the title. We added the word Riemann in the title, and it went through like this in Nature Communication, so powerful of Riemann. So it took actually 2 years to get published on this. Okay, so I'm going to illustrate what is these 2 experiments, and I will not say much about the theoretical foundation you can find in these papers. Actually, the first one was very important by Big Baef, And another important paper is by Gennady L. Back in Physicati back in '95. And also it was a beautiful review by Mark and Gennady a few years ago. Okay, so these are the physical problems. So the first one, let's have a look. We call dam breaking. So you have water separated by dam. The water on the right is higher than the water on the left. You remove the dam and you see what's going on. And this is actually equivalent to the shock tube problem. So a gas with two different densities, a diaphragm here, you remove the diaphragm, and this is equivalent to dam breaking. Second experiment is piston. So actually, you know that if you have a gas with constant density and you push with a piston, you create a shock. And if you retract the piston, then you form a rarefaction wave. But instead of doing this experiment with a physical piston, we replaced the physical piston with an initial condition. And the initial condition is in the velocity. So if you have a jump in velocity and the velocities are directed like that, you get actually a mirror image of this shock. So you get two shocks, and the two shocks separates going in opposite direction. If you have a situation, sorry, the shock is in this direction, the rarefaction is in this direction, you generate a mirror image of this, and you get two rarefaction waves. And what you expect? You expect, of course, that when you go into the dispersive regime, these two shocks becomes dispersive, and these two rarefaction remain the same because they are very smooth. They are smooth solutions, actually. And Peter Engels mentioned yesterday, actually, they had a similar experiment in BEC, in Bose-Einstein condensate, but actually the outcome is very different because, as far as I understand, they didn't observe the same dynamics we observed in optical fiber because it was dominated by dissipative effect in BEC. I don't understand why, so we could discuss about that. Okay, maybe very, very briefly, this is a sketch of the original paper by Gennady, 95. So you draw the sketch of all the possible Riemann invariant, how they behave. The important thing is that, I don't go through this, but the important thing is that you can outline the boundaries between the case. So you start from two rarefaction wave that can have or not a vacuum point in between. You go to shock wave, rarefaction wave, shock, and I will comment about that later. Okay, so instead of doing the mathematics here, I'll give you a graphic interpretation of this. Okay, first of all, you start with 4 parameters in your initial condition. So you have a left and right jump in U, in frequency, and in power, rho. But instead of having 4 parameters, which makes your life very difficult, you reduce to 2. And the way you do is that you assume you have a symmetric jump in U, and this is not loss of generality because a non-zero average means that you just tilt your dynamics, nothing essential. And you normalize 1 to the power to 1. So your parameters are only U0 and ρ0, and so you have a parameter plane. In this parameter plane, you can outline all the regions. So this is rarefaction wave, separated or not by a vacuum point. These 2 regions are dispersive shock wave, rarefaction wave, and this is dispersive shock wave, and this I will comment again in a minute. Okay, so. We designed 2 experiments. The first experiment is actually cutting this plane horizontally, and this is dam breaking. So cutting horizontally at U0 0 means to have only a jump in power, in density, actually. And what is important here is that Wheaton theory predicts the onset of cavitation exactly at the threshold for ρ0 equal 1/9, 0.011. And we want in the experiment to have a look, a quantitative look at this point. So whether or not in the experiment you find this. This is a quantitative agreement with Wheaton. And the second experiment is actually we cut vertically. So in this case means that you don't have a jump in rho, you have only a jump in velocity or frequency. And again, what is important, this is a piston problem, what is important here is this point. This point was predicted by Bibkaev, and it's actually a point u not equal to, where the dispersive shock and the dispersive shock here in this region are separated by a constant background that you can predict from the hyperbolic system. And instead, at this threshold, they are separated by a periodic unmodulated wave. That means that actually this is a rather extreme dispersive hydrodynamic state that you cannot have in a standard fluid. Because in a standard fluid, you can have this state with classical shock. So here, this shock with dispersion becomes dispersive. You expect that, but you don't expect that. I mean, it's rather surprising. At least it was to me. Okay? Okay, so let's go to the first experiment. So this is dam breaking. This is a simulation of the NLS. I'll show movie now, not equations. So you can see that actually there is what appears here is the blue is the input. Of course, what appears here is an intermediate state. And this you can predict from the hyperbolic system. And this intermediate state is connected to the upper state with the rarefaction, to the lower state with the dispersive shock wave. Okay, so far so good. This is the global picture of what happens. This is the output after a certain distance. This is in dimensional units of the experiment. And so you can recognize actually in the time distance plane that you can have three fans. The left one is a dispersive shock wave, which is expanding this fan. The second one is a plateau, the intermediate state. And the right one is actually the rarefaction wave. And Wheaton predicts exactly these velocities here, 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 and here. And they are in pretty good agreement, of course, with NLS, even though we are not in the asymptotic in a strict sense. And this black line is the velocity of the classical shock on which you do dispersive regularization, actually. Okay. This is important. Okay. Now, what I show in this movie is not the propagation, but is actually what happens when you move your initial condition in the parameter plane by this red dot. Okay. So starting from here to 0. Okay, so you can see, let's start again from 0. So you can see the rho naught status going down, down, down. And you can see the dispersive shock wave is becoming stronger and stronger, if you wish. Still, you have this intermediate state. And you can see at some point, 1/9, you get the cavitation in this point. And the cavitation then moves along the shock as you decrease rho naught. And at the end of the story, let me see. Sorry. At the end of the story, when you have what is called actually the when rho naught goes to 0, you can see that the shock disappears, and what remains is only the rarefaction. And this is very well known because it's what people teach in hydraulic engineer courses. When you have a dam breaking with dry bed, downstream there is no water, you cannot have a shock. In order to have the shock, you need to have water downstream the dam, okay? So this is important. And I want to make one remark, because once we actually illustrated this to an hydraulic engineer, and what I've shown you was the black curve, which is a classical solution of the hyperbolic system, and the blue one, which is the NLS, the dispersive regularization. He told me, OK, but the black line is wrong. Why is wrong? Well, it's wrong because actually there are two ways to solve the hyperbolic problem. One way is to use simple waves, so-called simple waves of hyperbolic problem, and one is going right, one is going left, to match that. And you get exactly the plateau here, the black one. But the other one is to impose vectorial ranking-Louvergneaux from the beginning. This is actually called in hydraulic engineering the Stoker solution. And actually, this is the physically admissible solution in the sense, and it's the red one, in this sense, okay, if rho naught is big enough, then the two solutions, the black one and the red one, are pretty much the same, no difference. As you decrease rho naught, then you can start seeing the difference here. But why this is the right solution? Because when rho naught goes to 0, what remains of the red is only the rarefaction. And this must be the case, okay? But what happens is actually for the dispersive people that we are, actually the black one is the right one because it gives the right prediction in terms of the intermediate state, actually. So in other words, the NLS wants to follow the black, not the red, okay? And the black predict that when rho naught goes to 0, the classical shock is still surviving, but as you do Wheaton averaging, then the amplitude of the oscillation goes to 0. So you retrace again the only rarefaction state. Pretty tricky at the time I went through this, but now we understand that. Okay, so that was the experiment, and I think I will go very, very quickly through. So actually, this is a generic experiment we want to do is with the wet bed, so water left and right are present. But since you want to do also the dry bed case, then you design a pulse which is like this in rho. Okay, so on the left, you have the wet bed dynamics, and on the right, the dry bed dynamics. I don't have to go through this. That was the experiment, but just to show that, in fact, you launch pulses with this shape. And the other feature I want to call your attention on is the fact that actually you need to make this problem a true conservative settings. And this is easy in fibers because you can exploit what is called Raman amplification. So you send another beam backward in the same fiber, and this is actually you set this beam to compensate the losses which are naturally in the fiber. The losses are really low. So we are talking in fibers about 0.2 dB per kilometer. The fiber is 15 kilometers, so you have more or less 3 dB, but 3 dB is enough to spoil the dynamics of the Riemann problem. So you need that. Okay. Okay, so this is the outcome. So this is the input pulse, and this is the output. You can see the intermediate level, the upper state, which remains the same, and the bottom quiescent state, and the dispersive shock wave is here, and the vertical dashed line are the Wheaton velocity. So pretty good much agreement about that. And this is the NLS numerics. So now we want to challenge further the Wheaton theory, as I said, and we changed what we call the dam height parameter, which is nothing but rho naught. We call it, sorry about this change of notation, it's called R in these figures, which is power to the left state and the power to the right. So left is this and right is this. Okay, so as you can see that, let's start from left. As we decrease these parameters, the dispersive shock wave becomes more pronounced, and at certain point you get cavitation here. Okay, the black is the numerics and the blue is the experiment. And as you keep on decreasing this parameter, then the cavitation points move along the shock. And the other feature I want to call your attention on is this. So on the dry bed case, you get only rarefaction as expected. There is some deformation, of course, because it's an experiment. Okay, this is a detailed zoom of the transition. Again, blue is the experiment, black is the NLS numerics. As we decrease this parameter R, so the dam height, essentially. And you can see that this a zoom around the bottom, the bottom state of the shock. So here you don't have any cavitation. You start to see cavitation in this picture, which is exactly the threshold predicted by Wheaton. And as you keep on decreasing this rho naught, you can see that this point is shifting toward left as expected. So we checked actually that the point, the experimental point, which are these, follow the Wheaton theory, which is this curve, which starts again from 1/9. So pretty much satisfied by the agreement with Wheaton. If you do the same for the this is a slide for the water wave people in the audience, and what I was able to find is the experiments in flumes for the dry bed. So the dry bed you consider rarefaction pretty well. But I'm not aware of very good results for shallow water for the wet bed case, because essentially when you do the wet bed case, you run into turbulence and overturning and other phenomena. So if you know some results that have a better agreement with the theory, actually, please tell me. Okay, so second experiment, again, I'm going to show movies, actually. So this time we have a constant power and we have a jump in velocity, so in frequency, actually. And you can see that this is the outcome as far as the point moves vertically on this phase plane, on this parameter plane, actually. So let's start again from the bottom, where you can start to see rarefaction waves, two rarefactions. When you reverse the sign, you start to see two dispersive shocks separated by a constant. And when you go to this threshold, which is again predicted by Wheaton theory, which is U naught equal 2, then you can see that actually there is no constant state between the two shock waves, but actually they are connected by an unmodulated periodic wave. And I'm going to show the next slide, the same movie, but done with Wheaton theory. And what I report here is same parameter plane, and again, you have to look at that, which is the rho. And here is the Riemann invariance of the hyperbolic problem, essentially. So again, you can see rarefaction with vacuum, then the vacuum disappears as you move vertically. Then when you reverse the sign of the step, you get two dispersive shock waves separated by constant state. And as you move here, you can see there is an unmodulated wave here, which is very interesting because it means that actually you start from two shocks like this, which are separated by constant state. They tend to merge as you keep on increasing the push of the piston. The U naught is the force, the velocity of the piston. They tend to merge, and as they merge, what they do? Well, in principle, you don't know. And the intuition by Bife was to tell, okay, let's assume, and in my opinion, this is an assumption, but it's probably right, that the dynamics is still one phase, so genus 1. And the only way you can satisfy the picture with the Riemann invariant is with a periodic wave in between the two shocks. And we wanted to actually measure this. So this is actually a very technical slide, so I will go very briefly, then you can ask me who is interested. How you generate the piston, actually, the jump in velocity, in frequency, actually, in our field. Okay, an easy way to do is to use a phase modulator, but you cannot use a phase modulator because phase modulators are either slow or cannot give you the jump that you want. We wanted at least 10 to 20 gigahertz, which is a lot for a modulator. So we actually use it in an optical way. And I'll give you only the flavor. So the flavor is the following. You start from, well, the first beam, which is the one you launch. This is the fiber where you do the experiment. You have another fiber before the experiment, high nonlinear fiber. So you launch here not only the constant power beam that you want, but also another color, another beam, which has this shape in time. So it's essentially an M shape or a 10th shape, okay? Why? Because this beam is going to give, through cross-phase modulation, through a term like this, a phase jump, actually not a phase jump, a phase modulation, where the frequency is actually the derivative of this shape. So the derivative of this shape changed by sign is either descending or ascending step. So it's an all-optical way, quite complicated, but at the end of the day, it was successful. And here are the results. Okay, so first, if this is a spectrogram, so how the frequency goes in time. So essentially, you have a jump in frequency at time equals 0, and the jump can be 10 to 20 gigahertz, as I said, and it's very, very abrupt. I mean, it's a Riemann problem we want to have, so it's a few picoseconds. And this is the occurrence of the rarefaction waves. This is 175 milliwatt, which corresponds to minus 63 in U naught. You decrease the power means that you increase the velocity of the piston, actually, and you get this rarefaction wave. Okay, one remark is the following, I forgot. Okay, the experiment is very difficult. So at the end of the day, you should have a constant power in a finite, of course, in a finite interval of time. But actually, you get a very noisy stuff, and this noise is affecting your experiment. Actually, you can see from the spectrogram that in both cases, so this is the descending or ascending jump, these are the M shape and the 10th shape, the switching is very abrupt. The price you pay is this noise on the top that should be flat and is not. And this effect of, this effect of course, the shape here that is expected to be flat, like in the numerics, and it's not, but it's an experiment, after all. And this is the case of the, it's jumpy. Sorry about that. Is this, perhaps? Again, not my fault. Technology is taking over. Okay, so let me see if I can use only the, yeah, not like that. Is there, yeah, better. Very good old days in Los Alamos. Okay, so this is a descending step. You can see that what you generate is actually two symmetric shocks. And this is the NLS simulation. The blue is the input one. As you decrease power, again, means to increase the velocity of the pushing piston, of the two pushing pistons, actually the virtual pistons. And you can see that you can, the two shocks becomes closer. You still have a flat top in between. But as you cross U naught equal to 2, that means going very low power, you don't have a flat state here. So essentially, this is a transition that Wheaton theory predicts. And the transition is where you get essentially the cavitation of the two shocks here. And we realized finally that actually the same setup can be used to do the most general problems. So I have the frequency step and the power step together. So this is the input, essentially. And this is the output. So this is experiment again and the simulation in the NLS. And we, again, increase U0. And we increase U0, we are here. So ρ0 is 0.15 in this experiment, just to cross the border between the dispersive shock wave with the constant state in between and the periodic wave. And you can fairly clearly see that actually this transition occurs. Okay. So last 10 minutes, I guess, I would like to switch on a different problem and give you some hint. Okay, so the problem is the following. Let's go to the focusing NLS now. And the focusing NLS, of course, has in the semi-classical regime a catastrophe. This catastrophe is different from the defocusing one because it occurs at time equals 0. So let's send a bell-shaped pulse or bell-shaped beam, and you generate a very steep gradient in velocity. So essentially, you put a force in the density, which is like this. The beam goes in this cusp-like fashion. It breaks, and then you have a periodic structure here. And also, if you do the periodic problem, you get the same. Okay, now if you do the hyperbolic dispersionless limit, this was realized, but actually in the 1970 by Gurevich and co-workers, actually, that is equivalent to a gas with negative pressure, so very anomalous stuff. And the reason of this minus sign is also responsible for modulation instability in this system. We know it has modulation instability. So the dispersionless problem is elliptic, is ill-post, is a bad guy in a sense, okay? But nevertheless, this problem was studied by many authors. Actually, Dubrovin, Grave and Klein give a very, very important work. Tobis, Vinakidis doing also. And I focus on the one of the 2013 actually result by Bertol and Tobis. They actually used similar to Dubrovin and co-workers, the Pine level 1, the three-truncate of the Pine level 1, to demonstrate actually that if you go into the epsilon equals 0 limit, and you are close to the catastrophe point, so close to here, what you generate here is a rational solution of the so-called peregrine solitons, okay? Rational solution of the focusing NLS. And actually, there's a lot of guys here also in the audience, Stéphane Randou and with Pierre Souret, and it was actually the thesis, PhD thesis by Tican. They demonstrated this experimentally. So essentially, they measured the peregrine profile with two different experiments in modulus and phase, and the experiment was very beautiful and very convincing, except one thing, that this is in the limit epsilon to 0. And the experiment has a number of solitons which is inverse of epsilon 2.2, so very far, which in one sense you can say, okay, it's very remarkable because you take an asymptotic result and you extend to the finite epsilon regime. But then there are two controversial issues here, which I want to discuss a little bit. So the first one is from our paper 2007. Okay, as you move to epsilon 0, the modulation instability gain grows, and also its bandwidth grows. So it becomes a huge gain. And what you expect? You expect that in this situation you get filamentation, not catastrophe. You get this, okay? Except now, if you take, instead of taking a local NLS, as I've written, if you introduce non-locality in your system, then the non-locality inhibits the modulation instability, and you get back to the catastrophe. So actually, our point was, if you are epsilon close to 0 in the local limit, you will never see the catastrophe, except you can see the catastrophe in the non-local case, okay? And the other issue is this paper by Jason Flesher, where they claim in the non-local case that actually they observed the picon profile. So picon is a solution of the very famous Camassa, Holmes, and other equations. But you don't expect that here, okay? So actually we can have 5 to 7 minutes, like that. 8? Let's compromise. Okay, so the experiment by Eric Louvergneaux was actually made in a nematic liquid crystal, so a strongly non-local system. And in this system, low power, you get diffraction. You increase power, you get a soliton. The soliton is called nematicon because the response is nematic liquid crystal. And if you keep on increasing power, you get a catastrophe point here. Okay, so they did the experiment. They injected the Gaussian beam. What they observe increasing power is this. So essentially, and this is seen from the top of the crystal, so you see the scattering, not any sophisticated imaging. But you can see here that at few hundred milliwatts, you get a catastrophe point, and then the beam opens up. And if you actually increase power, the catastrophe point shifts at lower distances. So you can have a plot of the catastrophe distance versus the power. Here is the experiments, the dots, and the fitting is power to the minus 0.64, whereas in theory you expect power to the minus half because of scaling of epsilon, essentially. And this is okay, but the important thing is that they actually look at the profile here, and you see again a picon profile. So something is puzzling here because you don't expect picon even in the non-local NLS. So we made some modeling, and the modeling is based on a non-local model. So the model is a nonlinear Schrodinger equation where you couple to a diffusion equation, and the non-local parameter is sigma squared. This is equivalent to a non-local NLS of this type where the kernel is Lorentzian, and this is a good approximation to this problem. So let's get rid of the second controversial, picon. So if we do the simulation in this model, and this is the same model we use for the thermal nonlinearity, then you can see if I take the profile here, the profile of the beam is a blue one, so it's still peregrine. So peregrine is correct, and peregrine survives the loss of integrability because it is a strongly nonlinear, strongly non-integrable case in the large sigma case. But if you get a look at the red is psi, which is a refractive index profile here. And so what you are seeing with picon profile is actually the refractive index, not the field, okay? So far so good. The other problem is the following, which is much more difficult. Filamentation versus catastrophe. What do you expect to observe? Okay, so we did some modeling, and you can show that actually the shock distance Zs depends on sigma, is not dependent on epsilon, as you expect from the hyperbolic limit. Sorry, the problem is no longer hyperbolic, from the elliptic limit, from the dispersionless limit, I should say. And you can give a very simple scaling. So essentially, the distance scales linearly with sigma, increases with sigma. And then two observations which are not trivial. If you keep sigma epsilon constant and large enough means bigger than 10 to the minus 3, so even small is okay. The dynamics happens to be the same once z is rescaled to zs. So essentially, zs changes because of this rule, but you can get a look at the dynamics. Here, the catastrophe is at 40, here is at 10, here is at 3, 2.5. Whatever, but the dynamics remains identical. And you see the catastrophe. This is a catastrophe point, okay, where the peregrine is. Now, if you lower sigma, the product sigma to epsilon, then you have a completely new situation. The situation is where the catastrophe goes into filamentation, and the transition is always at sigma between 0.05 and 0.1. Okay, so essentially sigma 1 catastrophe and regular. Even you couldn't see much, but it's regular, I can promise. Here you decrease and you can see some, of course this is a simulation with noise, which is the situation you have in experiment. Start to see some mess, let's call it mess. And as you keep on decreasing sigma, this filamentation gets in very strongly. And so this is the final slide. So essentially we made a chart of the dynamics, and in logarithmic scale you have log of epsilon and log of sigma. So essentially in the vertical direction you are more non-local in the going up, and whereas nonlinearity increases going to the left. Okay, and so these lines actually are simulation made with sigma epsilon constant. And sigma epsilon, as you can see, these free lines are always actually in a situation where you see the focusing catastrophe. If you go up to this line, then you see a single soliton, nematicon, not catastrophe. Okay. So essentially here you get the focusing catastrophe is observable. But if you get lower, and you can get lower by going sigma epsilon, again constant, but lower value, 5 to the -4, then you have a transition from the catastrophe to the modulation and instability. Modulation and instability means filamentation, so disordered breaking due to modulation and instability, okay? So essentially the experiment is here. So it's correct that in the experiment they do see, I mean the experiment in the nematics, not the experiment in the fiber. It's correct that they do see the catastrophe. And so at the end of the day, we did this to actually say what I said in the former workshop 2012. And this is a challenge to the theorists, the real theorists, mathematician, not me. It's okay in the local case, as you get really semi-classical, so low epsilon. Can you see what the results of Bertol and Tobis? So means a regular focusing point described by the peregrine? My answer is no, because you are operating in this regime here. And in order to see the result of Bertol and Tobis, you have to move to larger epsilon. And this is the reason why the experiment by Pierre Stéphane and Alexis worked. Okay, so that was the message. And sorry, 5 minutes, it's okay. So take-home message very briefly. Optical fibers have weak nonlinearity. I didn't mention that, but is well known. For they are the ideal playground to test fundamental problems of dispersive hydrodynamics, and I've shown this, showing that you can implement the first quantitative test of dispersive Riemann problem, actually. There are other media in nonlinear optics, and nematics is one of them, but it's not the only one. There are thermal media, there are very different media I didn't mention, which are useful to explore other regimes, and we use that to discuss this issue of the focusing catastrophe, and thanks a lot for the attention. Open to questions.
So I'm sorry there is no time for questions. We have to take a group photo. Okay, good. There's a group photo now, and of course a coffee break. So I would say if you have questions, let's do it offline and during the coffee break. Okay. Thanks, Stefano, for
Thanks, Roberto.